Assalamualaikum and greetings. My name is Aiman, matrix number 171666156, and today I'll be presenting to you about the KIB3011 project for using the Atmega 328 microcontroller for applications in medical field. In this case, we'll be using for sleep apnea detection. Now, first and foremost, I will introduce you to the project. This project aims to develop a sleep apnea detection system using the Atmega 328 microcontroller inside the Arduino Uno. The key objectives of this project include using an input interface, which is the FSR402 sensor, which is a pressure sensor, a data processing for apnea detection, and also the output interfacing for real-time feedback using the buzzer, green and red LEDs, and the LCD using the I2C. The sleep apnea is a medical condition characterized by interruptions in breathing during sleep, and the force sensor will be wrapped around the chest to detect the expansion of the chest to detect their breathing. Atmega 328 module has several key features in which it is useful for us in terms of utilizing its functions. It has a 8-bit AVR RSC architecture. It has a clock speed up to 20 MHz. However, commonly we use 16 MHz in standard Arduino Uno configurations. It has a 32 KB flash RAM. It has 2 KB SRAM and 1 KB EEPROM. Its peripherals, it has ADC, which is an analog to digital converter, which we'll be using today. Timers or counters, they have 3. They have the I2C and serial interface. They also have the digital input and output. They also have interrupts, where they different interrupts. They have external, pin change, timer, and also the analog digital converter interrupt. And lastly, it also has a PWM or pulse width modulation channel for pulse width output. Starting with the input interface, we are using the FSR402 force sensor, which detects force exerted during breathing by the expansion of the chest. So when it's connected to the Atmega 328 using the analog pin or the pin A0, or in this case ADC0, it will convert the analog signals which come from the sensor into digital values for processing through the necessary registers. The ADC conversion time depends on the ADC clock frequency and the number of ADC clock cycles, denoted by TADC, FADC, and NADC. Hence, we need to calculate them. So first, we find out the clock frequency by using the frequency of the microcontroller at 16 MHz and its max sampling size, which is in this case 128. We will get 125 kHz for the clock frequency, and for the conversion time, we will take the frequency, and then we can put it in the formula to get the amount of time for the conversion taken. In this case, 104 microseconds. Now for the ADC configuration, for the reference voltage, we set using the AD mux register in this project, as we use the default internal 5V reference, which is the REFS 0-bit set. And for the another one is the prescaler, which determines the ADC clock frequency, affecting the sampling rate and resolution of the ADC. A prescaler value of 128 using the ADPS2 or ADPS1 or 0-bit set. It is commonly used for accurate readings in range of 50 to 200 kHz. Now here and listed below is the according necessary C code for the input interface. After the input interface, we have to process the data through several methods. In data processing, the algorithms analyze the sensor data to detect apnea events. We use thresholds and timer-based checks using the necessary registers. So the system identifies the apnea episodes. The first method, by using thresholding and event detection, we have threshold calibration, real-time data acquisition, and threshold comparison. So when we calibrate the sensor to define what is the threshold for normal and apnea breathing, we will then have the real-time data acquisition, and then we will compare it to the thresholds that we have set within the code. The other method for data processing we have is timer-based apnea detection, whereby we use the timer setup and the interrupt handling. So as you can see from the code, we use the timer in order to interrupt the program when it indicates that the time period for apnea detection has passed, and so it interrupts the program to show that apnea is detected. Hence, it will display on the LCD. But this is the processing stage. Next, we will move to output interface. For the output, we have three things, which is the LED indicators, the buzzer, and an LCD display to provide real-time feedback. The green and red LEDs indicate a normal or apnea events respectively, and the buzzer alerts during apnea, and the LCD displays the breathing status. And as you can see from the C code, we include the LCD library, and then we define their address and columns, and then following that is the code to initialize it and also to reset it once it has displayed. Lastly, we have the discussion and conclusion, whereby we discuss what can be further improved and what are the challenges we face during this project. For the system performance and accuracy, we can improve it by using having better sensor integration and calibration. The FSR42 is a good sensor for sensor. However, if the that we can utilize a more sensitive sensor in which we can also ignore the need for calibration, it would be more independent and less likelihood for variation. And also the algorithm efficiency, whereby we can improve the time in the interrupts, whereby the detection can be faster. But which comes to the challenges and solutions, whereby we first and foremost we have the hardware limitations due to the analog digital converter resolution. With better microcontrollers, we can have better resolutions which can convert it faster, hence better real-time responsiveness. And lastly, for the future enhancements, we have again enhanced sensor technology if we have a better sensor utilized in this project. And to further improve this project, we can also have data logging and analysis by integrating the registers of a Wi-Fi module or a Bluetooth module, or also data logging and analysis, whereby we can store it somewhere. And lastly, better user interface improvements, so it can display the information better. That is all from me. Thank you so much.